Looking deeply inside nature through the magnifying glass of science, designers extract principles, processes, and materials that are forming the very basis of design methodology. Bionics explores the interplay between biology and design. As you can see, my legs are bionic. My bionic limbs are attached to my biological body via synthetic skins with stiffness variations that mirror my underlying tissue biomechanics. To achieve that mirroring, we first developed a mathematical model of my biological limb. To that end, we use imaging tools such as MRI to look inside my body to figure out the geometries and locations of various tissues. We also took robotic tools. Here's a 14 actuator circle that goes around the biological limb. The actuators come in, find the surface of the limb, measure its unloaded shape, and then they push on the tissues to measure tissue compliances at each anatomical point. We combine these imaging and robotic data to build a mathematical description of my biological limb, shown on the left. You see a bunch of points or nodes. At each node, there's a color that represents tissue compliance. We then do a mathematical transformation to the design of the synthetic skin, shown on the right. This is a material developed by SRI International, California. Under electrostatic effect, it changes stiffness. So under 0 voltage, the material is compliant. It's like floppy like paper. Then the button's pushed, a voltage is applied, and it becomes stiff as a board. Across my residual limb are electrodes that measure the electrical pulse of my muscles. That's communicated to the bionic limb. So when I think about moving my phantom limb, the robot tracks those movement desires. This diagram shows fundamentally how the bionic limb is controlled. So we modeled the missing biological limb, and we've discovered what reflexes occurred, how the reflexes of the spinal cord are controlling the muscles.